everyone. So we're going to continue our discussion of linear motion, talking about what's called scalars and vectors. Now, if you recall, we left off talking about how we had two different things that to talk about when it comes to measuring the length of a path traveled. We could talk about the distance, which was something that always kept going up and didn't really care about direction or the end result. It just really cared about the path we took. And then we had something called displacement, which was only looking at where we started, where we ended, and it actually did take into account direction. That leads into these two concepts. See, it turns out that there are some measurements that we talk about in this class that are considered scalars and some that are vectors. So these are categories that measurements can be put into. Um, So a scalar is used to define a measurement that only gives magnitude. Now in this class, magnitude is referring to size. Think back to what I said about the scientific notation and how the order of magnitude was basically how big the number is, the number of digits essentially. Here it's kind of the same thing. Magnitude just means size. So good examples are height. Height is something that's a scalar because you say that you're 6 feet tall. You don't normally say a direction to it. You don't say I'm 6 feet to the right. Age is another scalar because there's only a value. There's no direction. It's 10 years old and that's it. Saying that you walk 30 miles is again a scalar because that's distance. Vectors, on the other hand, have are measurements that give both magnitude and direction. So basically, you can add a direction to it and have it make sense. So saying that something is 3 miles to the east, that makes sense. That's a vector. Saying that you go 100 miles per hour westbound is another vector. So all of these are vectors. Now, the reason we mention this is for a few reasons. One of the reasons is because you are, again, guaranteed to be asked a question on the regions that is essentially identify the scalar and identify the vector. So these are going to be some common scalars and vectors that we're going to be using in this class. So the scalar terms are distance, speed, mass, time, energy, power, and voltage. These are the most common, though there are tons more. And for the vectors, there's displacement, velocity, acceleration, force, momentum, electric field, and magnetic field. For the most part, these are actually the only vectors we talk about. There are probably some other things that we mention in this class, other measurements that could be thrown in the scalar side, but for the most part, these are the vectors. Now, there's one tip that I can give. I do want to say that it doesn't work all the time, but it will answer a majority of these scalar vector questions. But if you notice the phrasing, the words used on this side, they're fairly simple words. They're words that most kids would understand. Kids know the word distance. Kids know the word speed and mass and time and energy. These are all things that they know. They're simple words. Scalar, simple. Look over here on the vectors. These are more complex words. Displacement, velocity, acceleration, force, momentum. Not really words that most kids would do. Now, there are, again, I said that this will answer a majority of questions. A lot of times they'll use a specific type of energy, which of course a kid wouldn't know. But the whole idea is just remembering that it's a type of energy. So that's what makes it a scalar. So simple scalars. Here, I'll even write it right over here. Scalars are simple. Again, this is a phrasing, a thing that you can use to answer some of the questions, but don't think that this is guaranteed 100% of the time. There have been a few times where kids got a question wrong trying to use this, and I said it's not a definition of a scalar, it's just a way to kind of identify most scalars. Now, you may notice in here that some of these are color coded, in particular distance and displacement, and speed and velocity. That's because these are what we call scalar vector pairs in the fact that they measure the same thing. So distance and displacement basically measure the same thing, but distance is a scalar form of length and and a displacement is a vector form. Same thing, speed is a scalar form of how fast you're going, and velocity is a vector form of how fast you're going. So this has popped up a few times where they say, which ones are the scalar vector pairs, and you just kind of have to recognize that that just means which ones are the same. Um, One easy way to remember vector, the term and what it represents. If you've ever seen this scene from Despicable Me, I'm not going to play it right now, but it's where Vector, that's what this evil villain's called, introduces himself for the first time. He explains why he calls himself Vector, and he basically, it sums up to his crimes are committed with both magnitude and direction, size and direction. That's what a vector is. Now, that's just the overall, like, what is the difference between scalars and vectors. We want to talk a little bit more about vectors because vectors have very unique properties. They're actually used very heavily in math, so they end up being a huge mathematical thing. And we're going to constantly be referring back to a lot of these vectors, but we're going to end up covering a lot of it right now. So first off, because of the fact that vectors are measurements that have an inherent direction in them, what we can do is actually represent them by using an arrow. So the length of the arrow is used to represent the magnitude or the size, and obviously the direction it points in represents the direction. Uh, because of this, we can do things like drawing scale diagrams to represent how one vector is bigger than the other by literally drawing it bigger. And if we have this drawn properly using a ruler, we can identify exactly how much bigger this one is compared to this. Just from the look of it, this we would say is probably 2 times the size of this. So the value is probably twice as much. If this was 100, this would be 50. That's pretty much it. Um, Now, when we have measurements that are vectors, this is actually one of the most important parts. When we have multiple measurements that are acting on an object and all of them are vectors, the way we add them is different because, again, direction matters. Now, we sort of actually started doing this a bit when we were talking about distance and displacement, though I didn't really put a name to it. In fact, some of you probably did it at home naturally by yourself without realizing what you were doing. So one of the ways that we can add vectors, when we combine them, we get what's called a resultant vector. So the resultant vector is just the sum of the vectors that we add, essentially the result of the vectors. Now there's two ways to combine vectors. The first way is done graphically. When that means drawing it out. And whenever we draw vectors, we need to make sure that the vectors that we draw are drawn what's called tip to tail. Now, if you recall, there was the one question before about a person going 4 blocks south, 3 blocks west, and then 4 blocks north. And the drawing I gave, and probably drawing that most people drew, looked something like this, where you kind of drew out pretty much a map of what happened. This is what we mean by tip to tail. You draw an arrow going this way, then the moment you finish drawing that arrow, you draw the next arrow, and then from there you draw the next one. Again, you're drawing a treasure map. This is different than if you had arrows drawn like this, which sometimes the regents will give to you because they want you to redraw this tip to tail. So this is not tip to tail. This is tip to tail. All right. Now we'll do a quick practice with this. So you can kind of do this at home. I recommend that you have a ruler or something on hand when you go to do this. but we're going to draw a 1D tip to tail method type question. So it's only going to be going in one dimension, either left and right or up and down. So the problem that I have is I travel 5 meters east, 10 meters west, and then 3 meters east. And I want to know what is the final displacement. Now, for the most part, this is a basic question. You probably wouldn't do what we're about to do on a question like this. It's a fairly simple, some of you can probably do it in your head. But the whole point is I'm trying to build up to the more complex questions. So the first step that we have to do is we have to determine a scale. Because of the fact that we're drawing a picture, we need to make sure that the vectors that I draw to represent 5 meters east, 10 meters west, and 3 meters east are drawn properly to represent that. Of course, I need to make sure that it's actually able to fit on the piece of paper. So a common example of a good scale would be a 1 centimeter to 1 meter, because this would fit on the paper. But of course, you might have to do something different in order to make sure it fits. Maybe you might have to do 1 centimeter equals 2 meters or something like that. Once you get the scale, then what you do is you pick a start. If they don't tell you what the starting point is, then you can pick one. But for the most part, there will always be some starting position, start at this location. So from there, you're going to draw the vectors to scale. So, and then also make sure to label them. So for example, I traveled 5 meters east, so I'm going to draw an arrow that's 5 centimeters, because 1 centimeter equals 1 meter, 5 centimeters east. From the tip of that arrow, I would then draw 10 meters west, and then from the tip of that arrow, draw 3 meters east. So that's my drawing. From here, I then draw my resultant line. Now I said before that these vector lines have to be drawn tip to tail. These vectors are drawn tip to tail. The resultant, however, is not part of that thing. It always goes from start to finish. So I started here, I ended here. It should pop up in a second. So here it goes from start to finish, and then what we do is kind of go backwards now. We now measure the line and then use our scale to figure out what it represents. So here, if you draw it out properly, you'll find that it should be about 2 centimeters long, which according to our scale means it's 2 meters. So my final displacement will be 2 meters west. We could do the same thing for a two-dimensional case. In fact, this is actually where it becomes a lot nicer. Um, it is a little bit trickier to do finding the resultants when you're going east, west, north, and south. Combination of that. So in a case like this, doing it tip to tail is significantly easier. Add to that there are cases where maybe one of these is going off on an angle, so it's not going north or east, it's going northeast. Again, that's where this method really shines. And it's done the same way. You draw a tip to tail, you draw a line going from start to finish, and the length of that line will represent your resultant vector. All right. Um, and again, usually in these cases, you always have to make sure you add a direction to it. All right. So practice this question, and we'll go over it in a second. All right, so in this question, we have a person that goes 10 meters west and 4 meters north. And we want to know, well, what scale should we use? Again, the scale could be different for each person. I think in this case, because 10 centimeters could fit on a piece of paper, we could get away with a 1 centimeter equals 1 meter. So we could go 1 to 1. But you could have gone 1 centimeter equals 2 meters, 1 centimeter equals 3. You most likely wouldn't have gone lower than 1 though. This is probably the biggest scale that you could use. All right, the next question is, what is the magnitude of the person's displacement? So we go 10 meters west and then 4 meters north. So what you should have gotten is 10.77 meters about. Now some of you may have actually done the math on it. That's fine, but again, we just want to try to get practice drawing the line and measuring it. Usually in a question like this, you're given a little leeway in the um, the actual answer. So some of you may have gone 10.9, some of you may have gone 10.5. I think pretty much anywhere between that, you would probably get credit for. So anywhere between 10.5 and 11, I believe, would be within reason. And then the next one, what's the direction of the person's displacement? Well, again, he went 10 meters west and 4 meters north. So he ends up going northwest. And that's pretty much it. All right, now these are some questions that I want you to think about yourself. So, why might this method not be accurate? Is there a reason why maybe this isn't the best method to use? The second one is, do you think we would get more accurate results if we used a bigger drawing or a smaller drawing? And then the third question is, does the order matter? So I want you to think about all three, and we'll go over in a second. All right. So the first one is, why do you think this method not be as accurate? Now, unfortunately, at this point, what I would have done is in the few questions that we've done, I would have pooled everyone's questions and answers, and you would have seen that everyone kind of gets a slightly different number. So one reason why this method might not be as accurate is maybe when you're drawing the lines, you're not drawing them perfectly horizontal. Maybe when you go north, you actually drew it a little bit off to the side. Of course, it wouldn't be swervy like this because you'd have a ruler. So that could be one reason that the instead of it drawing perfectly 90 degrees, you have a little bit of an angle. Or I've had kids do something like this where this line's drawn, but then they have an arrow off here, and then they start the next one from there. So there's always some sort of mistake that people will make in drawing it. So that's one of the reasons why this could be an inaccurate method. Now the next one is, which one do you think is more accurate? Well, the bigger the drawing, the more accurate the results. Because what turns out is that by having a much bigger scale like that, it'll make it so that any small mistake isn't ballooned up and blown up when converted. Like if you have a really tiny diagram like this, then the smallest mistake in you drawing this, when it gets scaled back up to the what each number represents, it will end up resulting in much bigger error. So you typically want to try and get the diagram as big as possible in order to get the best results. Now, this question, does order matter? Well, it turns out it does not. Now, I can give a very quick example. So let's say you go horizontally and then you go off on an angle like this. So your resultant, let me use a different color, will go from start to finish. Of course, my drawing is really bad, so it may not look perfect. Okay, there we go. Well, I can get to this same location by going this same distance this way first and then going this way. Oh, look at that. I just created a parallelogram. So yeah, it actually turns out that the order that you do doesn't matter. It doesn't matter if you go south, east, and then north, or south, north, and then east, or whatever. I usually have a simulator where I can show this. So if you want, in class, I'll probably end up showing you it. It's really nice and it really kind of gets the same idea that no matter which one goes first, no matter the order, you always end up in the same spot. So I know that the video is going a little longer than normal, but I just want to get to this part. It's pretty straightforward. As I said before, a lot of the one-dimensional questions, it's overkill to have to draw it. So I just want to quickly mention the addition method. So basically, when we add the two vectors, what we end up wanting to do is add them mathematically in one of these simple cases. And in fact, once again, most of you probably already did this without even knowing it. So the first step that you have to do is group like directions. What I mean by this is that you're grouping things like north and south directions, east and west, left and right. These are like directions. They're directions within the same dimension. So north and south is going, up and down, and then left and right, all those things. That's what I mean by grouping like directions. The next step you do is you define positive and negative. So you're gonna we when you have the directions for north and south, you're going to define one direction to be positive and one direction to be negative. Uh, for the most part, it doesn't really matter which one you choose. You can do whatever ends up making life easy. Like, for example, if you're for the most part going to the right, then you would want to make right positive. But if you're instead going mainly south, then maybe south should be positive. But usually, convention is that north, east, right, up are all positive, south, west, left, and down are all negative. Now, if you're confused as to why that is, think about a graph. So, in your graph, let's say you have, this is your x direction, this is the y direction. Which side on the x direction is positive? This side. And which side on the y direction is positive? This side. If I turn this into a compass, then this direction is north, this is south, this is west, and this is east. So the reason why north and east and up and down are positive is the same reason that they're positive on a graph, because that's what convention says. So that's one thing that you can kind of remind yourself if you're wondering why are we choosing these directions as positive. It's because of math. That's pretty much it. But again, you can choose whichever one you want. You just need to make sure you're consistent. You can't have some of your south directions positive and some of them negative. It's either you do all of them positive or all of them negative. Then what you're going to do is now add them all up. And whatever the resulting sign is, that tells you direction. So going back to our original example, I travel 5 meters east, 10 meters west, 3 meters east, and I want to know what the displacement is. Instead of drawing it out, what I would say is I would just go through each one of these terms, give them a sign. So I don't have to group like directions because these are all like directions, east and west. So now what I'm going to do, I'm going to use the convention that positive is east, negative is west. So 5 meters east becomes plus 5 meters. 10 meters west becomes negative 10 meters. And 3 meters east becomes plus 3 meters. Once I have this, I go to step 3 and I just add them up. Positive 5 plus negative 10 plus positive 3 gives me negative 2. And then from there, I know that the displacement is going to be 2 meters west because of this negative sign. And that's it. This is how you would normally approach one-dimensional questions by just adding them. So you can practice that on this one real quick. So pause the video, work on itself, and we'll go over in a second. All right, so trying to figure this out, we don't have to do the like directions. What we're going to do instead is assign values to this. So in order to find the distance, I don't actually care about these directions, so I'm going to add them up completely. So 40 plus 20 plus 10 plus 22, and I get that my distance is 92 meters. Now for the displacement, I need to put the signs where they belong. So 40 meters east, this is a positive number. 20 meters west, that's going to be a negative number. 10 meters west makes this a negative number, and 22 meters east makes this a positive. So I'm going to have positive 40 plus negative 20 plus negative 10 plus 22. And I end up getting my displacement 32. Because the final answer is positive, that means it's to the east. And that's it. Now, I'm not going to go over two-dimensional. We'll discuss that in the next part. So right now we're talking about linear motion, so going in only one single direction. While you should be able to do two-dimensional graphing with vectors, we'll talk about how we're going to do it the mathematical way in a bit. But for the most part, some of you probably will already know how that's done. All right. If you have any questions, let me know. Otherwise, I'll see you later.